Now, before diving into solving first-order differential equations, first take a look at the course description and objectives to understand what we will cover in this lesson. In this course, we will focus on ordinary differential equations, with particular emphasis on first-order differential equations and the methods to solve them. Throughout, by the end of this course, the student will be able to classify and apply various classical methods to solve first and second order ordinary differential equations and deduce solutions for related real-world systems. Before we start solving differential equations, we need to ask two fundamental questions. Does a solution of the problem exist? If a solution exists, it is unique. These questions are important because not all mathematical problems have solutions, and sometimes they may be multiple solutions. A well-posted problem in differential equations must satisfy two key conditions. A solution must exist. The solution must be unique. Now let's begin with the introduction to differential equations. A differential equations is an equation containing the derivative of one or more dependent variables for one or more independent variables. This one presents the general form of differential equations. Here y is the dependent variable and x is the independent variable. One important characteristics of a differential equations is its order, which is determined by the highest derivative in the equations. For example, in this case, the highest derivative is the first, then the order of this equation is first. The highest derivative of the equation is second, then the order of the equation is second. Before we define linearity, it's important to note that we can express derivative in different notation. For example, we can here write the derivative of y with respect to x as either derivative of y over dx or y prime. In nth order of ordinary differential equation is said to be linear if it follows this general form. To be considered linear, the dependent variable y and its derivative are of the first degree. This means the power of each term involving the dependent variable y is equal to 1. Another important condition is the coefficient depends at most on the independent variable x. The following coefficients depend at most on the independent variable x. As an example, here y and its derivative is 1, which satisfies the first conditions. The coefficient of y is 1, which is a constant. The coefficient of derivative of y with respect to x is 5x, which only depends on x. Then this equation is linear. In this example, we have 6x power 2. This equation is still linear because the exponent is applied to the independent variable x, not to the dependent variable y. This does not cause a problem. The problem arises only when the dependent variable y or any of its derivatives appears with a power different from 1. Now I will discuss nonlinear equations. As I mentioned before, an equation is not linear if one of two conditions is not met, such as a case where a term involves y in a nonlinear way, like sin y, exponential y, ln y. Here the power of the dependent variable y is 2, but different to 1. Then directly this equation is nonlinear. Now let's explore some common methods for solving differential equations. Depending on the structure of the equation, we can use different techniques to find solutions, such as separable variables, linear equations, exact equations, solution by substitutions, reduction to separation of variables. In this lesson, I will focus on explaining the method of separable variables. Now let's discuss the method of separable variables, which is one of the easiest ways to solve differential equations. Start with the general form. A separable differential equations is an equation that can be rewritten so that all terms involving y are on one side and all terms involving x are on the other. In particular, if f of xy depends only on x, it's mean f of xy equals g of x, then the equation simplifies to the following form. We can integrate both sides to find the solution. Y equals the following integral of g with respect to x. Let's apply the separable variables method to solve a basic differential equation. We are given the following equation. To solve, we integrate both sides with respect to x, then y equals integral of 1 plus e to x. We get the following solution. Y equals the integral of 1 is x, and the integral of exponential to x is 1 over 2 e to x, because that integral of exponential alpha x dx equals 1 over alpha exponential alpha x plus constant. In this case, alpha equals 2, then the integral 1 over 2 exponential to x plus constant. As I mentioned before, separable differential equations is a type of equations that can be rewritten so that all terms involving y are on the one side and all terms involving x are on the other. This means that we can separate the variables and integrate both sides individually. We can take this example of separable equations. We can separate each variables, then take the same form of separable equations. But here, this equation is not separable because y and term involve x are added together. The following equation cannot take the form of the separable equations. Another example, when we can use the method of separable variables, we are given the equation. We can separate the term involving y on one side and the term involving x on the other side by dividing each term by 1 plus x and y. Here we can eliminate y. Then we get dy over y minus dx over 1 plus x equals 0. Then dy over y equals dx over 1 plus x. This term involves only y and this term involves only x. Then we can integrate directly each term. We get the following expression because the integral of 1 over y is linear modulus of y. Also, the integral of 1 over 1 plus x is linear modulus of 1 plus x. We can recall the rule of the integral of 1 over y and 1 over 1 plus x. In general, the integral of 1 over u du equals linear modulus of u plus constant. To eliminate linear, we apply exponential on each term. Then linear and exponential are eliminate each other. We get y equals 1 plus x exponential c. Here, because exponential a plus b equals exponential a times exponential b, then exponential a, that's mean exponential linear modulus of 1 plus x, e and linear eliminate each other, then get 1 plus x times exponential c. We cannot exponential c by c. Now we are given initial value problem with initial condition. From the initial condition, we can find the constant on the solution. Like here, we can't find the constant c because we haven't initial condition, but here we can find the constant on the solution. At first, rearrange the term by multiply each term by y, eliminate y here. Also, we multiply each term by dx, eliminate dx here, find y dy equals minus x dx. This equation is separable. Then we can find the solution by direct integration. We obtain y2 plus x2 equals c. Can you recall the rule of the integral of y power n in general, dy equals y power n plus 1 over n plus 1 plus constant c. Here n equals 1, 1 plus 1, 2. Then we get y power 2 over 2 equals minus x power 2 over 2 plus constant c. We eliminate 2 by multiply the whole equation by 2. We get y power 2 equals minus x2 plus 2c. Then y power 2 plus x power 2 equals constant c. This one is the solution of this initial value problem. We can find the constant c by using the following initial condition. We replace x by 4 and y by minus 3. Minus 3 power 2 plus 4 power 2 equals c. 9 plus 16 equals c. Then c equals 25. After that, we can find y power 2 equals minus x2 plus c. Then y equals plus minus square root of constant C 25 minus x2. Why we choose the negative expression? Because the initial condition is negative, then the solution is minus square root of 25 minus x2. For this example, we are given an initial value problem, then we can follow the previous example to find the solution. I will explain the remaining methods and techniques in another lecture. In this presentation, there is an exercise that will help reinforce the concepts we have discussed. Finally, for further reading, I have referenced the following books, which were key sources in preparing this lesson. Thank you for your attention.